A tetrahedron ABCD is said to be angelic if it has non-zero volume and satisfies these two angle equalities shown on screen. Across all angelic tetrahedrons, what is the maximum number of distinct lengths that could appear in the set AB, AC, AD, BC, BD, CD? So what is this problem asking us? Well, we have these two angle equalities here, so let's see how we can interpret them. So one of these is angle BAC plus angle CAD plus angle DAB, and that is this angle here plus this angle here plus the angle in the back. So you can think of this as the sum of the face angles at A. And this is the sum of the face angles at B. And then we also have the sum of the face angles at C and the sum of the face angles at D. And we want to find the number of distinct lengths that could appear in this set here. And one way to think of this is just the set of all tetrahedron side lengths. So that means that if we have a regular tetrahedron, then all of these lengths would be the same, and that would give 1. But surely we can do a lot better than that. And we wish to find the maximum number of distinct lengths. So how can we start on this problem? Well, we already have our face in the back, and that makes it complicated because we can't really deal with angle BAD without doing some weird stuff. So we should try unfolding the tetrahedron. So this is our unfolded net. And in order for this to even be a net, it has to satisfy many properties. For example, these two red lengths must be equal because otherwise when we fold up BC and BD, A1 and A2 do not align. And similarly, these two green lengths are equal, and so are the blue lengths. So now let's determine what our angle equalities mean. Let's start with this one here because this one might be a bit messy because we started unfolding from A and we have these separate angles. Luckily, the second angle condition translates into something really simple, and it's that this angle here is equal to this angle here. And why is this true? Well, because angle ACB, which is A1CB, since this is our face ABC, plus angle BCD plus angle DCA is this angle. And this angle here is angle ADB plus angle BDC plus angle CDA. So now we know that these two angles are equal. So let's see what the other angle condition turns into. So we have that the sum of this angle here plus this angle here plus this angle here is equal to this angle here plus this angle here plus this angle here. So the sum of these angles here really calls for us to use some sort of sum of angle identity. And this here is a hexagon, so we can use the sum of the angles in the hexagon. So I'm going to put this angle in here to be orange. And I'm going to put the remaining angles inside blue. So the sum of the blue, and then we have plus the orange, and then we finally have the purple, is equal to 720 degrees. And now we know that the orange is equal to the blue. That's our given angle condition. So we have that 2 times the orange angle plus, and for the purple, we know that it is just twice of that one angle. So it's 2 times purple 1, and that's equal to 720 degrees. So therefore, we know that orange plus purple is equal to 360 degrees. And what this means is that this angle here, the exterior angle, is also the purple angle. So now we have our angle conditions, and they are equivalent to the following facts. This angle is equal to this angle is equal to this angle here. With these angle equalities said, let's now solve the problem. So we have that these two angles are equal, as we said earlier, and we also have that these two lengths are equal, and so are these lengths. So that means that these two triangles here, this one here and this one here, are similar to each other. So this means that triangle A1B A2 is similar to triangle A1C A3. Now, this is a spiral similarity. So by spiral similarity properties, this also implies triangle A1BC is similar to triangle A1A2 A3. Now, A1 A2 A3 is a pretty symmetric triangle as it does not involve any of BCD. But A1 BC does not involve D at all. So we could try applying it on the other 2 points A2 and A3. So let's try it. If you apply the same process on A2, we have that these two lengths are also equal. So by a similar argument, since these angles are equal, we have triangle A2D A3 is similar to triangle A2B A1. And again, by spiral similarity properties, this means that triangle A2DB is similar to triangle A2A3 A1. Or if we want to combine both of these similarities into one, we have triangle A1BC is similar to triangle A1A2 A3 is similar to triangle BA2D. Now, can we apply the same thing on A3? Well, we have these lengths are equal again, but these two angles are facing each other. So a spiral similarity does not exist centered at A3 in this case. So now we have that this triangle here is similar to this triangle here. So these two triangles here. But they have an equal edge, namely this red one, which means that they must be in fact congruent. And since they are congruent, that means that BC is equal to the green edge. Let me go ahead and draw that. And this also means that BD is also equal to the blue edge. And now we only have one possible side length left. And if we color pink, suppose, for another distinct side length, we only arrive at 1, 2, 3, 4 distinct side lengths. And that's the maximum that we obtained. So the maximum is less than or equal to 4. And if we want to show that it's equal to 4, then we just need to find a construction that works. So let us do that right now. Now observe that BC is equal to DA3 and BD is equal to CA3. So BCA3D is a parallelogram. So we can redraw our diagram so that this is the case. So now we have our parallelogram here, BCA3D. And now let's show that this satisfies the angle equalities. Because this forms a valid net because of these length equalities. So we can always fold it back up and retrieve our tetrahedron. So first let's check that angle C, the sum of the angles at C is equal to the sum of the angles at D. And in order to prove this, we can note that this angle here is equal to this angle here since they are parallel. And also this angle here is equal to this angle here. And finally, this angle here is equal to this angle here. So therefore, all of them correspond, which means that angle C is equal to angle D. So now let's show that the sum of the angles at A is equal to the sum of the angles at B. So we have that this angle here, by congruent triangles, since A1BC is congruent to B2AD, so this one here is congruent to this one. Then this one here, so by the parallelogram is equal to this one here. And finally, this one here is equal to this one here, but again by the congruence. So therefore, we have that these two, the sum of these three angles here, which is this here, is equal to the sum of the angles here, which is this expression here. Therefore, this tetrahedron net satisfies all the angle equalities and has 4 distinct lengths inside the set, specifically the red, blue, green, and pink. And we can make what the red, green, blue, and pink lengths whatever we want, so long as they satisfy the triangle inequality. And when we fold our tetrahedron back up, this gives us our angelic tetrahedron. And therefore, the answer to this problem is 4. So what did we take away from this problem? Well, one thing to note is that whenever you have a tetrahedron and you want to examine properties about its faces, a good idea would be to unfold it. And the reason for this is because you want to figure out how the faces behave. And when you try looking at it in 3D, you can't really examine a face in its entirety because it would be hard to mark angles. Another thing to learn from this problem is that always recognize spiral similarity when it appears. For example, we notice a spiral similarity sending BA2 to CA3 centered at A1, and that showed that A1BC is similar to A1A2A3, and that's also similar to BA2D, and that basically solves the problem. So be on the lookout for spiral similarities. And that's all I have to say. Thank you so much for watching this video. Please subscribe if you'd like to see more videos.